We are standing outside the door to the Physics Funhouse right now because today in the Physics Funhouse, we're going to try to explain how doors work. I know what you're thinking. You already know how to work a door. You just walk over here and you pull on the handle, right? Well, it helps if you unlock it first. But the question today in physics is, why is the handle over there and not over there? Here's the hinge over here. Like that silver bar thing is the thing that holds the hinges in place. Why is the handle of a door always located on the other side of the door from the hinges? That's the question we want to answer today in the fun house. Okay, so I found my keys, so now I can kind of show you guys how to open a door. And you probably instinctively know, because you may have messed this up as a small child and eventually figured out how to do this right, that when you want to open a door, especially a heavy door like this one, you push over here at the edge, and it is easy to open the door. If you try to open a door by pushing on the inside edge, like over here close to the hinge, it is much more difficult. There it goes, to open up the door. And so the further out on the door you push, the easier it is to open the door. So today we want to be able to explain why that is. Why is it easier to push over here on the door to open it than to push over here on the door? So the word of the day today is the word torque. Over here, you can generate more torque with a small force because you're further away from the pivot, whereas when you are close to the pivot, you have to exert a larger force to get the same amount of torque. And so our physics word for the day is torque. So in order to be able to explain how a door works, we need to understand the concept of torque. Torque is the amount of force, so we're still thinking about what makes things move, how they interact, that could cause a system to rotate. And so I have such a system right here, where I've got a meter stick that is suspended from a universal physics clamp, patent pending, from a pole that is stuck in this stand right here, and I've got that universal physics clamp right in the center of the meter stick so that it hangs there, it is balanced. It doesn't rotate one way or the other. And so right now there are two forces acting on it, the clamp itself and then weight pulling it down. Neither of those forces is providing a torque at this moment. Neither of those forces could cause this thing to rotate the way the system is oriented. So if I wanted this meter stick to rotate, I could exert a force over here. That force would exert a torque, causing the meter stick to rotate. One thing that we need to understand about torque is that where the force goes matters. So for instance, if I push on this side of the meter stick upwards, I get a rotation in one direction. And if I push on the meter stick this way, upwards, on the other side, I get a rotation in the opposite direction. And the direction for rotation is either clockwise or counterclockwise. So an upward force on this side of the meter stick causes a counterclockwise force. An upward force on this side of the meter stick causes a clockwise force. And so where the force goes matters in determining not only the direction of the torque, but also the magnitude of the torque. So torque is forces that could cause a system to rotate. Next, let's get into how the position of where a force is exerted changes the torque. So there are three factors that determine how much torque a force exerts. The first would be the size of the force. That should be obvious. So if I push gently, I get a little bit of rotation, whereas if I exert more force, I get more rotation. That should be obvious. The second factor is where the force is exerted. We're going to do a little bit more careful demonstration here in a few minutes, but for right now, we can see that if I exert a force here, I get a little bit of rotation, whereas if I exert the force over here, I get a lot more rotation. So the position of the force not only determines the direction of the torque, but it also determines the size of the torque. And that's something that's going to be new for us. And then the third factor that determines the amount of torque a force exerts is the direction of the force. As it turns out, we're going to have a thing called a moment arm. And so for right now, the meter stick can just be its own moment arm. If I exert a force perpendicular to the moment arm, I get a torque and I get a rotation. If I exert a force parallel to the moment arm, I do not. And so even if this thing were free to slide along the universal physics clamp there, pushing parallel to the moment arm will not cause a rotation. And so we'll get into the mechanics a little bit more, like what do you do when it's in between? Pro tip, vectors are involved, and a few more careful demonstrations. So for right now, our starting point is that the three things that determine the size of a torque are the size of the force, where the force is exerted, and the direction of the force. So next, we're going to examine this where the force is exerted thing a little bit more carefully in a little bit more detail. Okay, so let's investigate this where does the force go thing a little bit more in depth. So here on the meter stick, you'll notice that it's in equilibrium. It's not moving anywhere, but it's not balanced anymore. It's not level. And the reason it's not level is because I took a second universal physics clamp, attached it to the meter stick over here, a distance r from the pivot point, and I hung a 50-gram mass from that universal physics clamp. And you'll notice that that torque that this is generating caused the meter stick to rotate. So instead of being flat level, it rotated clockwise to that position right there. If I slide this thing further away from the pivot point and then release it, you'll notice that it rotates even more. And so the further away from the pivot point the force is, the more torque it generates and the more rotation it can cause. So the next thing we're going to try to do is balance that torque by putting a force on this side, or I could put a force on this side but in the opposite direction. So I can exert an upward torque over here to balance the torque exerted by this thing to cause the net torque to be zero. So let's hang a second thing from here and then see how the two forces and moment arms compare with each other. Okay, so here we have a situation where we have two forces that are exerting torques on the meter stick. I've got a 50-gram mass hanging here, and I've got a 100-gram mass hanging here, and the meter stick is in rotational equilibrium. And so the clockwise torques are balanced by the counterclockwise torque. So this weight over here pulling down this way is causing a counterclockwise torque. This way pulling down on this side is causing a, this is causing a clockwise torque. This is causing a counterclockwise torque. And so you'll notice that the smaller weight is further out from the pivot point. That's what the rod is. And that distance between the pivot point and the point where the force is exerted is referred to as the moment arm. And so you can see that the smaller force is exerting the same amount of torque as the larger force because the smaller force has a larger moment arm than the smaller force. And so these forces are exerting the same amount of torque even though they're not the same size forces, because the smaller force has a greater moment arm than the larger force. Next, let's investigate a situation where there are three forces exerting torques on the meter stick. So here's a situation where I have three forces acting on the meter stick that are exerting a torque. The 100-gram mass is exerting the same amount of torque as it was before because its moment arm is still the same as it was before. Like this piece of tape is the exact same piece of tape I used in the previous demonstration. The distance from the pivot to the 100-gram mass has not changed. Notice that the 50-gram mass is now over on this side of the meter stick. So what's the force that's exerting the third torque? The third force that's exerting a torque is the weight of the meter stick itself. Before I had the meter stick balanced in the center, and so its force had a moment arm of 0. Like the weight and the pivot point were acting at the exact same point. Now, the center of gravity, center of mass of the meter stick is not at the pivot point, and so it is exerting a torque. And so if we wanted to know the torque exerted by the meter stick, we would need to know its moment arm, and to do that we just have to find the center of mass of the meter stick. So the 50 centimeter mark on our meter stick is right here. And so the distance here to here of the meter stick is the moment arm for the force exerted by the weight of the meter stick itself. So in this situation, I've got the weight of the meter stick, which is medium, times a pretty big moment arm, balancing the force of the 100-gram mass, which is large, but a small moment arm, and then a small force with a medium moment arm. So all three of those torques are balancing each other. So now let's get into the mathematics a little bit and see if we can figure out how this relates to mathematical expressions of torque. Okay, so let's get into some of the mathematical details regarding torque so that we can use it to analyze systems of objects with multiple torques exerted on them. First of all, the symbol that we use for torque is the Greek letter tau, which kind of sort of looks like a T that somebody's beat up a few times with a hammer. And so when you draw it on a whiteboard, it kind of looks like that. When you print it in Microsoft Word using Times New Roman, it kind of sort of looks like this. And so don't write a T, because remember T still stands for tension and time and all those sorts of things. So practice writing the letter tau. You're going to write that letter a lot. So the mathematical definition of torque, torque equals force, because the size of the force determines the torque, times the moment arm, that's the where the force is exerted bit, and then the direction of force means that we only want the force that is perpendicular to the moment arm. And so F perpendicular times R, you could also put the perpendicular on the R bit, and we'll spend plenty of time working on the geometry of all that a little bit later. If you look into some physics textbooks, that would be written with an F and then like a cross symbol times R, which means the same thing, but the term cross product, which is what this is, F cross R, is a calculus term that we're not going to use in Physics 1. And so we'll say the perpendicular component of the force times the moment arm gives us the torque. By convention, we've all kind of agreed that positive torques are going to be counterclockwise torques, and I'll demonstrate that the reasoning for that a little bit later on. And so the example that we just did with the three forces exerted on the meter stick and the meter stick in equilibrium, the free body diagram would look something like that. And so when something could potentially rotate as a result of the forces exerted on it, we need to actually draw the object itself. And so we can't just draw a dot to represent our meter stick anymore. And we need to draw the forces at the actual position that they're exerted. So the gravitational force on the meter stick is at the center of mass, which is in the middle of the meter stick. The 100-gram mass, which would be 1 Newton, was exerted some distance R2 from the pivot, which was the rod. And then the 50-gram mass was exerted some distance R1 from the pivot, which again was the little rod in the middle. And so when we draw free body diagrams for things that could potentially rotate, even if they're not rotating, like the meter stick's not rotating, with those forces that are exerting torques that could cause it to rotate, we need to actually draw the object itself. We can't just draw a dot anymore. So next, let's set up a simple example and see what's necessary for this thing to be in equilibrium, and kind of get an idea of how to calculate the torque on something and then the net torque on something. Okay, so in this example, I again have three torques acting on my meter stick. The meter stick is again balanced at its center of mass, so the gravitational force does not exert a torque because it is at the point of rotation. It's at the pivot, if you will. And so R basically is 0 for the weight of the meter stick. Likewise, the force of the universal physics clamp holding it up exerts no torque because its moment arm is 0, R equals 0. I've got a 500-gram mass over here at this moment arm, so this is its moment arm. I've got a 200-gram mass here, so the moment arm for that one would be this distance right here, and then this far away from the pivot point, I've got a 100-gram mass hanging there. And so this torque plus this torque plus this torque all has to be adding up to 0 because the meter stick is in rotational equilibrium. So let's draw the free body diagram for this. Let's figure out the torque exerted by all three of these forces and see if it does in fact add up to 0. So I'm going to move this out of the way carefully. Okay, so instead of drawing the meter stick on the whiteboard, I've actually just taped a meter stick up there so that we can kind of sort of like get a good visual representation. And I've drawn all of these forces to scale, carefully using a ruler. And so that arrow right there is 5 times as long as this arrow right here, because this force is 5 times as large as this force right there. Scale, especially if you're using a piece of graph paper, that might kind of help you see the magnitude of all these things. Remember that the torque exerted is F perpendicular times R. And so all these forces are perpendicular to the moment arm. The meter stick is its own moment arm right now. And so I don't need to do any fancy vector resolution. We'll do that kind of stuff a little bit later on. The convention is that counterclockwise torques are positive. So what we're going to do is we're going to write a net torque equation, just like we would write net force equations back in the day. And when we do that, forces that are exerting counterclockwise torques are going to exert positive torques. Clockwise torques, we're going to make negative. So let's do a net torque equation. So sigma torque equals, and I'm going to kind of go in order from left to right across our meter stick. And so I'm going to start with F1, which is the 1 Newton force, which has a moment arm of 45.4 centimeters. And so if we kind of think, all right, which direction would this thing make that meter stick rotate? Remember that the pivot is right here. And you can kind of use a pencil or a ruler. I'll use a ruler since it's larger. I actually have another meter stick right here. If you have trouble seeing whether a torque is a counterclockwise or clockwise torque, you can take your pencil or something like that, hold it at the pivot point, push it in the direction of just that one force. And so the F1 over here is downward, and see what direction your pencil or whatever rotates as a result. And so this is rotating counterclockwise, and so this is going to be a positive torque. And so I'm going to write 1 Newton. And then because I want everything to be in our normal SI units, instead of centimeters, I'm writing meters. So times 0.454 meters would be the torque exerted by force F1. Let's do number 2. Number 2 is on the same side of the pivot as F1, and so it's going to also exert a counterclockwise torque, or a positive torque. So I can say plus 2 newtons. Its moment arm was only 21.8 centimeters. So again, making that meters will look like that. The blue force, F3, on the other side of the pivot is going to exert a clockwise force. And so if you have a pencil or something, you can hold in place at the pivot, push in the direction of the force where the force is. That would cause the meter stick to rotate clockwise. Clockwise negative, and so we'll say minus 5 newtons. And its moment arm was a teensy-weensy 17.7 centimeters. So converting that to meters, 0.177 meters. So there is our net torque equation. The torque exerted by force 1 plus the torque exerted by force 2 minus the torque exerted by force 3. Hopefully when we add these up we get 0, because the meter stick is in equilibrium. And I'm going to kind of do these one by one. So I'm going to write down the intermediate values so that we can see kind of how big all of these torques are. And so the first one, 1 times 0.454 meters would give you just 0.454. So the red torque is 0.454. And the unit is simply Newton times meter. Now, if you're trying to be clever and you think that that is a joule, because you remember work is force times distance, and the unit for work is joules, don't be clever and try to make that into joules. That's not a joule. When we write down the unit for torque, we have to write down Newton times meter, because this is a Newton and a meter perpendicular to each other rather than parallel to each other. So Newton times meter, don't think that you're clever in recognizing that that is a joule. It is if they are parallel to each other. these are perpendicular to each other. Okay, so and then plus, let's find the torque exerted by the red force. So if you multiply 0.218 by 2, you get 0.436 newtons times meter again. And so if you compare the torque exerted by the red and the green forces, they're pretty much the same, within 2/100ths of each other. And so notice that this is just a little bit more than twice that. So half the force, about twice the moment arm, about the same amount of torque. So doing the blue one now, minus, so we do 5 times 0.177, we get 0.885. 0.885, and again, that would be Newton times meter. All right, so now we can add those up. Net torque equals 0.454 plus 0.436 minus 0.885. And when you do that, you get 0.0. I'll show you how good that came out. 0.05. Our unit would be newtons times meters still. And within experimental error, like we're talking a millimeters worth of difference in our R values, which are kind of hard to measure because the clamp is wide. You got to get right in the middle of the clamp. That is equal to 0. And so when the torques on an object add up to 0, then it is in rotational equilibrium and it's not going to move. So if I were to have scooched the blue force out just a little bit more and made that torque larger, now the net torque would have been some negative number and it would have rotated clockwise. If I had moved the green one out further, then the green number would be larger and we would get a positive net torque and it would rotate counterclockwise. So let's demonstrate that real quick. So here's my meter stick with the 3 weights hanging on it again, and I'm going to take the 500-gram mass and I'm going to scooch it further out. So by moving this further out, I've increased the amount of torque it exerts. I'm going to hold it in place with my fingers. And so increasing R means I increase the amount of torque. And so the red number and the green numbers don't change. The blue number is bigger. I should get a net negative value, which means I should end up with a clockwise rotation. It's not rotating right now because my fingers are exerting a 4th torque on the meter stick, balancing it out. So when I release it, we should see this thing rotate clockwise. 3, 2, 1. There we go. It rotated clockwise. Now your next question might be, well, why does it stop rotating? Like, if it's got a net torque, it should continuously rotate and continuously speed up. And the answer is that now I've changed the direction of the forces. By having the moment arm, which is the meter stick, tilt, now these forces are not perpendicular to the moment arm anymore. So by changing the angle that the forces exert, I have changed the amount of torque that they exert. We'll investigate that again a little bit later on. But that's why it comes to rest. Otherwise, yeah, it would continuously speed up. But as those angles change, like when it goes straight up and down, it would exert, none of them would exert any torque. It'd be parallel to the moment arm. When the angles change, the torque changes. So let's do another example. Let's scooch this thing way in, right there. So by moving it inward, now the blue number is smaller, and these two are the same. So same size minus a smaller number gives me a net positive torque, which means I should get a counterclockwise rotation. So again, I have a 4th torque, my fingers holding it in place. And then let it go, let's see which way it rotates. And it rotated counterclockwise. And so our next step, after we do a lot of static torque, is to do dynamic torque. What happens when you continuously exert an unbalanced torque on something, causing it to speed up? So we'll do that after we spend a bunch of time dealing with just static torque, things in equilibrium. Okay, so hopefully the next time you encounter one of these door things, you now know what to do. Don't push over here. where you have a small moment arm, which will require a large force to exert the torque needed to open the door, push over here so that you have a big moment arm. And you can push like with your fingers and open up the door. So now you know how to operate a door, and you can explain why a door works the way a door works. Till next time, ta-ta.